Okay, we will discuss now the following problem. How to find a basis for a vector space. So essentially we have seen there are two different possibilities. The first possibility is that a vector space is given in explicit form as the span of some vectors in Rn. The second possibility is that our vector space is given as the set of the solutions of a system of homogeneous linear equations. In the first case, if it is given as the span of some vectors in Rn, we are in a better situation than in the second case. As we will see from this diagram, if we want to get the basis for a vector space given in implicit form, we have to go through all these steps. Suppose we are in the first case, so the vector space is given as the span of some vectors in Rn. Then, the procedure simply requires you to take these vectors and plug them into a matrix and compute the row echelon form of this matrix. Once you have found the row echelon form of this matrix, the vectors corresponding to the position of the leading ones, they form a basis for V. In the second case, the vector space is given as the set of the solutions of a system of homogeneous linear equations. In this case, we first have to solve the linear system and find the parametric form for all the solutions of the previous linear systems. Once we have the parametric form, we can replace this as the span of something, and then we simply call back the previous procedure. Let's see one example. Suppose we are given the following problem. We are asked to find a basis for this vector space. The vector space is defined in R3 as the set of the solutions of a system of homogeneous linear equations. In which case are we? In the second one, I guess. So the vector space is given in implicit form. So what do we have to do first is to solve the linear system. So let's find all the solutions to this linear system. We get these equations that are equivalent to the previous one, from which we get that all the solutions are of the form minus 2t t minus t. It means that we can plug in every value for y, and then x has to be minus 2y, and z has to be minus y. So all the solutions to the previous equation are of this form. But this vector is exactly t times minus 2, 1, minus 1. It means that the set of the solutions of this linear system, it is actually the span of this vector. So this step from here to here, it is exactly the function that we have called here once you have the parametric form of a linear system. So at the end, what we have is the vector spaces presented as the span of some vectors. In this case, there is just one vector, which is this one. So if you simply follow this diagram, it will be very easy to find a basis for a vector space. Let's see another example. We are asked to find an orthonormal basis for the orthogonal complement of W. So what we are asked is to find a basis which is orthonormal for the orthogonal complement of W. So the first step, we have to find a basis. Once we find a basis, we can apply Gram-Schmidt procedure. Okay, now we have to find a basis. For which space? The space we are interested in is the orthogonal complement of W. Let's name this space V. So as you see, V is the orthogonal complement of W. So V is presented by equations. The first equation requires the orthogonality with respect to the first vector. The second equation requires the orthogonality with respect to the second vector. So V is the orthogonal complement to W. It means that every vector in V has to be orthogonal to this vector and to this vector. So every vector in V has to solve the equation to be orthogonal to this, which is the first one, and the equation to be orthogonal to this, which is the second one. Now we have V written as the set of the solutions of a linear system. So what we simply have to do in this case is to call back our previous procedure. So what the procedure requires is to solve this linear system first and to find a parametric form for all the solutions to this linear system. I have found this parametric form for you. So all the solutions to this linear system are of the form 2t minus t as t. Now the procedure requires to go through this step, which essentially allows you to go from the parametric form to the explicit form. In this case, for example, this is the parametric form. We collect the t part and the s part into two separate vectors. And we get that this vector it is actually t times this vector plus s times this vector. This is exactly the definition of the span of this vector and this vector. Now we have presented V as the span of two vectors. So what we have to do to find the basis is simply do the row echelon form of the matrix obtained by plug these vectors into a 2×4 matrix. And this is the result we obtained by computing the row echelon form of the corresponding matrix. As you see, the leading one are in the first position and the second position. It means that the first vector and the second vector, they form a basis for V. Notice that this doesn't say this vector plus this vector, they form a basis. This step just allows you to detect which vectors among the one spanning V are actually a basis. Now that we have a basis, we can simply apply the Gram-Schmidt procedure and get an orthonormalized basis. Let's see now another example. You are required to find an orthogonal basis for the image of A transpose, where A is this matrix. So the exercise requires you to find a basis which is orthogonal for the image of A transpose. So what we want to do now, since we have to find a basis, we want to call the previous procedure. Once we will have the basis, we will apply Gram-Schmidt. The vector space in this case is the image of A transpose, which means that is the span of the columns of the transpose of A. Once we have put these vectors into the matrix, we compute the row echelon form. In this case, this is the row echelon form of this matrix. Now we look at the leading ones. They are in this position and in this position. It means that are in the first position and the second position. This says that the first vector and the second vector, they form a basis for V.